You're the fastest runner in history, but there's one little catch. You can't outrun a tortoise. It sounds like a bizarre joke, right? But according to an ancient Greek philosopher named Zeno, this scenario is not just possible, it's inevitable. In this mind-bending paradox, Achilles, the swiftest hero of ancient Greece, gives a tortoise a head start in a race. Confident in his speed, Achilles is sure he'll easily overtake the slow-moving creature. But here's the twist. No matter how fast Achilles runs, Zeno claims he will never catch up to the tortoise. How could this be? Zeno's paradox isn't just a clever riddle. It's a profound challenge to our understanding of motion, space, and infinity. Although we know from experience that Achilles should outrun the tortoise, Zeno's logic presents a conundrum that has puzzled philosophers and mathematicians for millennia. This is Zeno's Achilles paradox, a centuries-old puzzle that forces us to rethink the very fabric of reality. And in this video, we're not just going to explore how Zeno framed this paradox, but also why it still baffles minds today and how it connects to modern science. Around 450 B.C.E. in ancient Greece, a philosopher named Zeno of Elea posed a series of puzzles that would go on to confound thinkers for millennia. Zeno was a student of Parmenides who believed that reality is singular and unchanging, despite what our senses might tell us. He believed that all change is an illusion, which is at odds with our everyday experience. So, to defend this radical idea, Zeno devised paradoxes that challenge our very understanding of motion, time, and space. Among these, the Achilles paradox stands out as one of the most famous. Zeno's paradoxes don't just challenge the idea that many things exist, they also question whether movement, space, and time are even possible. Let's break down the Achilles paradox. Imagine a race where Achilles, the fastest runner in Greece, gives a slow-moving tortoise a head start. By the time Achilles reaches the tortoise's starting point, the tortoise has moved a little further. When Achilles reaches that new point, the tortoise has moved even further. This pattern continues indefinitely. Each time Achilles reaches the tortoise's previous position, it has advanced just a bit more. Zeno argues that Achilles will never catch up to the tortoise. It sounds absurd, but Zeno's logic appears flawless. Now picture yourself in a similar scenario. You challenge a tortoise to a 100-meter race and generously give it a 1-meter head start. By the time you cover that first meter, the tortoise has already moved ahead, perhaps by 20 centimeters. You cover that distance, but the tortoise has crept another few centimeters forward. No matter how fast you run, the tortoise always seems to stay ahead. According to Zeno, this infinite series of steps means you'll never win the race. But Zeno didn't stop there. He also introduced the Dichotomy paradox, which suggests that to reach your destination, you must first get halfway there, then halfway again, and so on, creating an infinite number of steps that seem to make motion impossible. Then there's the arrow paradox. Imagine an arrow flying through the air. At any single instant, it occupies a specific position in space, seemingly at rest. If time is composed of these instants, how can the arrow be moving at all? If everything is motionless at every instant, and time is just a collection of these instants, then motion itself appears impossible. Though these paradoxes were eventually addressed through advances in mathematics, they found new relevance in the strange and counterintuitive world of quantum physics. Zeno's puzzles remain a fascinating glimpse into the complexities of reality, reminding us that even the most straightforward concepts can harbor profound mysteries. Throughout history, Zeno's paradoxes have perplexed philosophers and mathematicians alike, pushing them to grapple with the very nature of reality. One famous story involves the philosopher Diogenes the Cynic, who, when confronted with Zeno's paradoxes, didn't waste time with a philosophical debate. Instead, he simply stood up and walked, effectively mocking Zeno's claim that motion was impossible. Diogenes' response was clever, but it sidestepped the real challenge: the logical structure of Zeno's arguments. To truly address these paradoxes, one must do more than just demonstrate that motion is possible. One must pinpoint the flaws in the reasoning that leads to these baffling conclusions. Aristotle and Archimedes, two of the most influential minds in ancient Greece, Each tackled Zeno's paradoxes in their own ways. Aristotle took Zeno's arguments seriously, offering his own interpretations and critiques. For instance, in the Achilles and the Tortoise paradox, Aristotle echoed Zeno's reasoning, noting that in a race, the quickest runner can never overtake the slowest, since the pursuer must first reach the point whence the pursued started, so that the slower must always hold a lead. Regarding the dichotomy paradox, Aristotle acknowledged the infinite division of space that Zeno proposed, stating that which is in locomotion must arrive at the halfway stage before it arrives at the goal. For the arrow paradox, Aristotle pointed out that if time is composed of indivisible instants, then the flying arrow at any given instant appears motionless. Yet he also suggested that if these instants are viewed as continuous, then motion is indeed possible. Aristotle also discusses other paradoxes of Zeno. For example, in the paradox of place, Aristotle argued that if everything that exists must have a place, then each place must also have its own place, leading to an infinite regress. Aristotle also addressed Zeno's paradox of the grain of millet. Zeno argues that if a single grain of millet falls, it makes no sound. However, if 1,000 grains fall, a sound is produced. This leads to the seemingly absurd conclusion that 1,000 nothings, individual grains making no sound, somehow combine to produce something, a sound. Aristotle responded to this paradox by challenging Zeno's reasoning. He argued that even if a single grain of millet does not make an audible sound by itself, it still displaces air when it falls. This displacement, though not perceptible to human senses, contributes to the overall sound produced when many grains fall together. Aristotle's response suggests that imperceptible events, such as the sound of a single grain, can accumulate to produce a perceptible event, the sound of many grains. Aristotle further criticized Zeno's reliance on the idea that 1,000 nothings could not add up to something. He acknowledged that sensory perception has limitations, and that just because we cannot perceive something does not mean it does not exist or have an effect. This critique highlighted the limitations of relying solely on sensory perception, a point that modern philosophers like Nick Huggett have expanded upon. Huggett notes that Zeno's argument is rooted in Parmenidean philosophy, which distrusts sensory perception, while Aristotle's response acknowledges that even faint, imperceptible events can contribute to a detectable outcome. Another paradox Aristotle tackled was the moving rows paradox, also known as the paradox of the stadium, where two rows of bodies move in opposite directions at equal velocities. Aristotle expanded on Zeno's arguments. He responded, "Concerning the two rows of bodies, each row being composed of an equal number of bodies of equal size, passing each other on a race course as they proceed with equal velocity in opposite directions, the one row originally occupying the space between the goal and the middle point of the course, and the other that between the middle point and the starting post. This involves the conclusion that half a given time is equal to double that time." While Aristotle believed that space and time couldn't be divided infinitely, Archimedes offered a different perspective. He introduced the concept of different types of infinities. For instance, the set of natural numbers like 1, 2, 3, 4, and so on is infinite, yet a finite interval on a number line, like 1 centimeter, contains an infinite number of points. Archimedes argued that although the distance between Achilles and the tortoise keeps shrinking, the time needed to cover these smaller distances also decreases. Ultimately, Achilles would catch up to the tortoise in a finite amount of time, resolving the paradox. Although Archimedes' approach to Zeno's paradox was insightful, he couldn't mathematically prove his reasoning. Archimedes was indeed correct. It took over 2,000 years before a rigorous solution was found with the development of calculus by Isaac Newton and Gottfried Wilhelm Leibniz. Calculus provided the tools to handle infinite sums and infinitesimally small quantities, showing that while you can divide a length into an infinite number of smaller intervals, the time required to traverse these intervals is still finite. Let's see how calculus solved Zeno's paradox. Let's break this down with a simple example. Suppose Achilles gives the tortoise a 1-meter head start, and Achilles runs at 12 kilometers per hour, while the tortoise moves 5 times slower. When Achilles covers the first meter, the tortoise has moved 20 centimeters ahead. When Achilles covers those 20 centimeters, the tortoise has moved another 4 centimeters, and so on. Achilles is trying to catch up with a tortoise, and the distance he needs to cover can be described as an infinite series of numbers. This series begins with 1, then adds smaller and smaller fractions, 1/5, 1/25, 1/125, and so on. At first glance, adding an infinite number of terms seems like it would give an infinite result, but calculus allows us to understand and sum these infinitely small quantities, known as infinitesimals. The important insight here is that even though the series goes on forever, its sum has a finite value. To find this sum, we can factor out the first fraction, 1/5, from the series. This lets us rewrite the series in a way that reveals a pattern. Specifically, we can express the series as 1 plus 1/5 times the original series itself. By recognizing this pattern, we create an equation that relates the series to itself. The equation tells us that the sum we're looking for, let's call it S, is equal to 1 plus 1/5 of that same sum, S. To find the value of S, we solve the equation. The solution shows that the sum of the infinite series is 1.25. In other words, Achilles only needs to cover a finite distance to catch the tortoise, despite the infinite number of steps involved. From this discussion, we see that while calculus provides a mathematical resolution to Zeno's paradoxes, the philosophical implications continue to provoke debate, inviting us to explore the very nature of reality, time, and motion. Zeno's paradoxes are thought to have been resolved with the development of calculus in the 17th century. Calculus provided a powerful tool to describe continuous change, offering a mathematical solution to the ancient contradictions posed by Zeno. From a scientific perspective, it seemed that these paradoxes had been laid to rest. However, the advent of quantum physics brought Zeno's paradoxes back into the spotlight, revealing new complexities that classical physics could not address. Particles such as electrons exhibit behaviors that defy classical understanding. One of the most intriguing aspects of quantum mechanics is how the mere act of observation can affect a quantum system. When a quantum system is observed, its state becomes frozen, preventing it from evolving naturally. In the quantum realm, particles are typically in a state of constant change. They can transition between different energy levels or move from one location to another. However, when these particles are measured repeatedly, the probability of them changing state diminishes. As a result, they become trapped in their original state, unable to evolve as they naturally would. This phenomenon is known as the quantum Zeno effect. In other words, the act of observing a quantum system can effectively freeze its evolution. For instance, if you repeatedly measure an unstable particle, you can prevent it from decaying by collapsing its wave function each time you observe it. This phenomenon echoes Zeno's paradoxes, where motion or change seems impossible due to the infinite steps required. In the quantum world, Zeno's ideas manifest in a modern context, showing that the paradoxes have more than just theoretical value. They have practical implications in the very fabric of reality. Physicists have confirmed the quantum Zeno effect through various experiments. By frequently measuring a quantum system, they were able to halt its temporal development, effectively freezing the system in its current state. This effect has practical applications such as in commercial magnetometers, where it helps maintain the stability of quantum systems used to measure magnetic fields with extreme precision. Interestingly, the quantum Zeno effect is also believed to play a role in the magnetic sense of birds, known as magnetoreception. Birds may use this effect to keep the quantum states involved in their navigation stable, allowing them to detect and follow Earth's magnetic field. This application of the quantum Zeno effect in biological systems highlights the deep connections between quantum mechanics and the natural world. Zeno's paradoxes also resonate in the study of space and time, particularly in the context of general relativity and quantum mechanics. Zeno's arguments about the infinite divisibility of space and time prefigured debates in modern physics about the nature of the universe. In Einstein's theory of general relativity, space and time are treated as a continuous fabric that can be curved and stretched by gravity. However, quantum mechanics introduces the idea that, at the smallest scale, space and time may not be continuous at all, but composed of discrete units, or quanta. The continuous nature of spacetime in general relativity and the discrete nature suggested by quantum mechanics represent two fundamentally different ways of understanding the universe. The challenge of reconciling these two theories, of creating a unified theory of quantum gravity, is one of the biggest ongoing quests in theoretical physics. One of the key issues in this pursuit is that general relativity and quantum mechanics work exceptionally well in their respective domains. General relativity in describing large-scale phenomena like black holes and the expansion of the universe, and quantum mechanics in explaining the behavior of particles at the atomic and subatomic levels. However, when you try to apply both theories simultaneously, such as in the extreme conditions near a black hole's singularity or during the Big Bang, the equations break down, leading to infinities and contradictions. Even 2,500 years after Zeno's original thought experiments, his paradoxes continue to captivate and challenge our understanding of reality. While calculus provided a mathematical solution to the problem of motion, the paradoxes still raise profound questions about the nature of our universe. How do the fundamental building blocks of our world move and change? What exactly is a measurement, and what does it mean to observe a quantum system? Is reality independent of our perception, or is it fundamentally shaped by the way we observe and interpret it? These questions remain central to both philosophical inquiry and scientific exploration, reflecting the deep and enduring impact of Zeno's paradoxes on our quest to understand the nature of reality. These questions remain at the forefront of scientific inquiry, and it may take millennia more to fully answer them. Zeno's paradoxes, it seems, are far from being completely resolved, ensuring that they will remain a topic of debate and inquiry for generations to come. Zeno's paradoxes continue to serve as a powerful reminder that our intuitions about the world can be misleading. They challenge us to reconsider our assumptions about motion, time, and reality, encouraging deeper inquiry into the nature of the universe. As we push the boundaries of human knowledge, Zeno's ancient puzzles remain a source of inspiration, proving that even millennia-old questions can have profound relevance to the cutting-edge science of today. In this way, Zeno's paradoxes are not just historical curiosities. They are living challenges that continue to provoke thought, drive scientific progress, and expand our understanding of the cosmos. As Richard Feynman said, "Not only do I not know what I am talking about, I am not even sure I know how to be certain that I don't know what I am talking about."